All right, welcome to lecture. We'll get started in just a second. We're going to continue on here in chapter 16, I think it is, talking about thermodynamics and delta G. So again, as always, if you have questions, please feel free to ask them below. We're going to lecture here today, and then at 11:30 during our normal lab time, you'll go and take your exam. It will be open at that point for you to take it. All right, so previously we started getting into sort of thermodynamics here. Again, thermodynamics deals with really the idea of, three sort of thermodynamic properties, delta H, which we've seen before, delta S, and delta G. So delta H is the enthalpy of a reaction, basically the heat of a reaction, as you learned before in previous classes and also in this class. Overall, the delta H value, if it's positive or negative, will give us some indication in terms of energy, sort of what is going on there. Is it an exothermic reaction if delta H is negative, which means heat and energy is being released? Is it an endothermic reaction, which delta H would be positive, to mean that heat and energy is being absorbed? Delta H really kind of deals with the first law of thermodynamics, kind of that conservation of energy. Energy is not lost nor destroyed, are created and can be transferred from one form to the next. Delta S, as we talked about last time, is entropy, not to be confused with enthalpy. This is entropy. And entropy deals with the idea of sort of the randomness and disorder of the universe. And when we have an increase in entropy, we have an increase in the disorder that's happening. And if we have sort of a decrease in entropy, that means we have sort of a decrease in the disorder or an increase in order, whichever way you kind of want to look at that. Again, delta S is a little bit different than some of the other ones there. Delta S, when the entropy increases, it actually gets a more positive value, while when the entropy decreases and things become more ordered, it actually becomes more negative. So sometimes it's a little bit backwards for people to kind of think about. We also talked about two ways you could calculate the entropy. You can calculate the entropy of a reaction by taking basically the products minus the reactants, the entropy values that you can find from a table. And just like anything else, you also want to multiply by the coefficient found in the balanced equation to those values that you find there. Also different with entropy in terms of those table values is you will find in the table some values for things like H2, O2, things in their natural state. So there are some values, unlike delta H, where those guys are zeros. In addition, in terms of units, entropy, delta S is usually given in joules, while things like delta H and delta G are given in kilojoules. So that's the delta S of the system or the reaction, which is oftentimes the same thing. We also talked about how to find the delta S of the surroundings, and the delta S of the surroundings is related to the enthalpy, the delta H, and it's equal to minus the delta H of the reaction over the temperature in Kelvin. And it's sort of the opposite relationship in terms of entropy, as we talked about under normal temperature conditions. If a reaction is exothermic, it would give off all that heat and energy to the surroundings. The energy that the surroundings would pick up would cause a lot more disorder, and we would expect a positive value for the surroundings. And vice versa, if the reaction, for example, was endothermic, needed to pick up the heat and energy from the surroundings would lose that heat and energy. Everybody would become more ordered, and the delta S would be negative in that particular case. We also saw that you can predict sort of the sign of the delta S of the reaction by looking at gas molecules. So the production of more gas molecules would cause more disorder, and thus would create a more positive value for S, and vice versa. If you end up on your product side with less gas molecules, that's then going to a more ordered fashion, and we would expect a more negative value. Using both the delta S of the reaction or the system and the delta S of the surroundings, you could add those together to get the delta S of the universe. Remember that the delta S of the universe is the sort of factor that you could use with delta S to determine whether or not a reaction is spontaneous or non-spontaneous. Again, if you calculate the delta S of the universe and it is a positive number, then the reaction will be spontaneous. If you calculate delta S of the universe and it's negative, it'll be a non-spontaneous reaction. And then we finished up last time here talking about delta G, which is Gibbs free energy. That again is energy available to do some type of work. And there's a couple different ways you can actually calculate the delta G. You can calculate the delta G just like we do S and H. If all you're given is the reaction, you essentially want to go to the table and find the values for the products and reactants and do products minus reactants. And just like everything else, you do want to take the coefficients into account and make sure that you multiply by them. Another way that you could calculate delta G is through this equation that we see here up on the screen, which is the delta G is equal to delta H minus T delta S. So this would be obviously the equation that you would use if you were obviously given some values like delta H or delta S, or maybe you calculated delta S and delta H, and you would put it into this equation. Unit-wise, though, as we did talk about, there are some differences. Again, this is going to be in kilojoules, and this guy is going to be in joules. So you do need to, especially when you use this equation here, do some conversion of the units. Otherwise, obviously, you'll be off by that factor of 1,000. Delta G, much like delta H, you'll have 0 for things in their standard state when you look them up on the table. The units of delta G are also kilojoules typically. So in the end, typically these guys are kilojoules as well. And we can use the value of delta G to help us determine whether or not a reaction will be spontaneous by calculating the delta G of a reaction, for example. And if the delta G value is negative, then that would imply that the reaction is spontaneous the way it's written. And if the delta G value is positive, it would be a non-spontaneous process. Any question on that stuff that we talked about last time there? Now, as I mentioned, I think last time as well, in this chapter, more so probably than any other chapter, you'll be asked a lot of questions where perhaps you may not be given any values or anything like that, but you may be told, hey, this is positive, this is negative, and that will help you determine whether or not, for example, the reaction would be spontaneous or not. So, for example, if we look at this sort of table here that's in your book, if we have a delta H that's greater than 0, so I'm assuming that means it's positive. And we also have a delta S that is positive. Delta G would be a positive number at low temperatures, and the process would only be spontaneous at high temperatures in this particular case. So we'll see why that is. So when we look at it, now again, because the value here of delta H is in kilojoules and our S is in joules, at normal kind of low temperatures, this back part of this number will always be smaller. This part of the number here in this situation will be smaller than the delta H value. And that means that when you do calculate delta G at low temperatures, you would expect it to be a positive number, and the reaction would not be spontaneous. Now, the only way to sort of reverse that is to get this part larger. And the only factor that will allow you to do that is temperature. So if you had a high temperature, and that may be enough to make that value larger than the delta H value. And so at high temperatures, we would expect to turn that into a negative delta G, and thus the reaction be spontaneous. Now, if we look at it and our And sort of the second situation there, our delta H is going to be negative, and our delta S is going to be positive. In this particular case, no matter what happens, because this guy is negative and this guy is positive, so this guy is also going to be negative, you're going to hit a negative number for delta G no matter what the situation is. And that means when you have a negative delta H and a positive delta S, pretty much that reaction should be spontaneous at any temperature because of that. Because no matter what temperature you throw in there, you will end up with a negative number. If our in this situation, our delta H is positive and our delta S is negative. What that's going to do is this is going to be positive. This negative and negative will turn this whole thing into a positive, which means no matter what you do at any temperature, it's going to be a non-spontaneous process. That's because delta G will always end up being a positive number in that particular case. And our last sort of combination here would be our delta G. Our delta H is negative, and in this box, our delta S would be negative. So this is going to be negative. This here is going to turn this side into a positive. So at this particular case, the delta G at sort of low temperatures and normal temperatures will be negative because, again, this part of the sort of formula is about 1,000 times less than what we got going here because, again, this is kilojoules and this is joules, right? So at lower temperatures, that box part will not be able to get larger than the delta H part, and you will end up having a you will end up having a negative value for delta G, and the reaction will be spontaneous at low temperatures. But if you're able to boost the temperature up high, it will turn that positive part larger than the negative part, and you'll end up with a positive delta G, and the reaction will be non-spontaneous. So you can kind of look at these formulas again and sort of decide if this is positive, this is negative, sort of what would happen in terms of the delta G value. Any questions on that? All right. So why don't you take a second here? Why don't you calculate the delta G naught here at 25 degrees Celsius, and why don't you see if it's spontaneous at that time? So take a minute or two, calculate the delta G based on that value at 25 degrees and see whether or not it's spontaneous, and then we'll talk about it. All right, so let us take a look here. And in this particular case, we are calculating the delta G, but we're given the delta H and delta S values. So this would be a situation where we would want to use the equation that we just saw, delta G naught equals delta H minus T delta S. Again, a reminder that the little kind of naught means sort of standard conditions. And again, it's usually kind of book type conditions, 1 atmosphere for pressure, uh, 25 degrees Celsius for temperature. If we're talking about concentrations, everybody's 1 molar and stuff like that. So because we're given the delta H and delta S values, we could just plug it into that formula. We'll have our delta H, which is 177.8. I here I'm going to times it by 1,000 to convert it to joules. You could leave it in kilojoules if you want, but again, at some point you do need to convert perhaps the delta S into kilojoules. So I'm going to leave mine though in joules because I converted the other. And if we do all that, we end up with 129.971 joules. Or again, at this point, you could take it to kilojoules like it normally is, of 130 kilojoules. Any questions on that calculation? So again, what we could see is at 25 degrees Celsius here, our delta G value is positive, which means this reaction would be non-spontaneous at 25 degrees Celsius. And that's what we would expect based on what we just saw. Our delta H is positive, our delta S is positive. So at low temperatures, like 25 degrees Celsius, this back part here is not large enough to overtake the front part, which is positive. So we end up with a positive number. Any questions on that there? Now, the nice thing also about sort of this equation as well is if you do discover, for example, like we just did here, that at 25 degrees Celsius, this reaction is non-spontaneous, you could also use this formula to figure out at what temperature it would become spontaneous. So we could use our same formula here to figure that out as delta G equals our delta H minus T delta S. What we know is for it to become spontaneous, our delta G here has to be negative, which means that's less than 0, right? So if we set that equal to 0 and we got delta H minus T delta S, bring it to the other side and solve for T, T would get us delta H divided by delta S. So we could actually use those values there to help us determine what temperature that would become spontaneous. So if we plug those values in, we get 177.8. Again, we have different units here, so I'm going to multiply it by 1,000 to convert it to joules. We're going to divide it by my 160.5, which are in joules. And if we do that right there, 177.8 times 1,000 divided by 160.5, that gives us 1,108. If you're wondering what the units of that is, it's right here. It is actually Kelvin. I'll spit that out in Kelvin. And if we subtract 273 from that to convert it to Celsius, we end up with a number of 835 degrees Celsius. So 835 degrees Celsius in this particular example represents the minimum temperature at which this reaction would become spontaneous. And if we look at our chart here in this reaction, this chart is the pressure of CO2 versus temperature. The reason they're following pressure is because pressure is a product, right? So in order for products to be made and pressure to be made, The only gas here is CO2. So we could follow basically the pressure of CO2. And since it's the only gas, when we start to see an increase in the pressure, we should know that we've made some product here, right? And that's what we do see if we look at this graph here. We do see at 835, that is technically when we hit 1 atmosphere, which is standard pressure, right? And you can see before that, it does start to rise a little bit, but it doesn't get to sort of that level of standard pressure until about 835 degrees Celsius. That also sort of reiterates what we saw when we were looking at that chart a second ago here with our positive values on both ends for delta H and delta S. At low temperatures, it will be non-spontaneous, but it will become spontaneous at high temperatures, and 835 degrees Celsius I would classify as a pretty high temperature, and that would be enough to turn this particular reaction into being spontaneous. Any questions on those calculations? So this equation is useful, obviously, in a few different sort of aspects. Again, you can use it like we did at the beginning, just to simply calculate something like delta G and determine whether or not this reaction will be spontaneous or not. But second to that, you could actually use this equation here and rearrange it and use it to solve for, okay, if this reaction is not going to be spontaneous at a particular temperature, what minimum temperature would this reaction basically turn to be spontaneous? Any questions on any part of those calculations there? All right, so why don't you take a second here and calculate this one. Following reaction, delta H is 1204 and delta S is minus 216. So at 25 degrees, are the reactants or products favored here? Perhaps calculate the delta G and see what you come up with and make sure everybody's calculator is working correctly. We'll talk about it in a minute or so. Okay, so let us take a look. So again here, like we talked about before, there's a few different ways to calculate delta G. I always say probably the best way is just to think about what's given to you. So in this case, we do have our delta H given to us and our delta S. So probably this would be sort of the right formula here. Technically speaking, they're all dots there, or knots. So again, we're just going to kind of plug it in here. And I'm going to, again, take my delta H and I'm going to multiply it by 1,000 and convert it. Again, you can leave it in kilojoules. You just need to probably convert the other one to kilojoules. We're going to convert our temperature into Kelvin, right? So that's 298. And I'm going to leave this in joules because I took care of the conversion on the other end. And if we do all that good stuff there, it looks like we end up with something like minus 1139512.8 joules. Kind of clean it up again. Delta G is usually in kilojoules, so we're divided by 1,000, and we'll end up with something like, looks like minus 1,140 kilojoules. Any questions on the calculation part? So remember that we can use this value to determine whether or not this reaction is spontaneous or non-spontaneous. And since our delta G is less than 0 or negative, it would tell us that this reaction should be spontaneous. So delta G is less than 0, which means it's negative, and it would be a spontaneous reaction. And since it's a spontaneous reaction, we would assume the reaction is heading to the right towards the product side. So we would expect products to be made in this particular case. And again, we could verify if this sort of makes sense based on what we've been talking about. Here, our delta H was a negative number. Our delta S was also a negative number. Remember, these two negatives on this side is going to turn this into a positive number. And here at 25 degrees, which is a low temperature, it means that this part of the equation here will probably be smaller than the delta H, and that should result in a negative number, like we saw. So again, you sort of understand that sort of relationship. It's just another way you could just check to make sure everything's okay in terms of calculation wise. Any questions on that? Okay. Now, there is free energy that happens at phase changes. And when we do phase changes going from, as we saw a little bit earlier as well, going from, say, solid to liquid, liquid to solid, as we talked about with heat, that's the heat of fusion involved there. There's also the delta S of fusion, right, which would take care of the entropy change that occurs. And going from liquid to gas and back to gas to liquid, that is typically for delta H, the delta H of vaporization that we use. And that's the delta S of vaporization is sometimes referred to. Now, just like normal, right, depending on which way you're going, if you're going from solid to liquid, the delta H is going to be a positive number. And if you're going the opposite way, the delta H, right, would be a negative number. And that relationship is sort of what we see as well as we go from solid to liquid. We would expect the delta S to be a positive number as we're increasing the amount of disorder, and our delta S heading in the other direction would be negative as we're creating more order. And the same thing happens as our liquid goes to gas and backwards. Again, our delta H is going to be positive here, heading in that direction, and our delta S would be positive and negative in the opposite direction, depending on which way you're going. So again, we can use this equation because what we talked about and what we know is when we do reach that point of where that happens. So for example, liquid going to gas, that's the normal boiling point for a substance. The solid to liquid is the normal freezing point. That is an equilibrium process, right? So exactly at 100 degrees Celsius, for example, for water, you have both steam and liquid water happening together at equilibrium. And that means that technically our delta G, if you remember, at an equilibrium process is going to equal 0. And that's going to turn this equation into one similar to what we just did, we could actually rearrange it and solve for delta S in this case. And that comes from rearranging this equation where 0 equals delta H minus T delta S. Bringing delta S to the other side gets you T delta S equals delta H. Dividing the T to the other side gets you to the one that we see down there, the delta H over T. Now, you may remember this equation, or one that kind of looks like it. This is very similar to the one that we saw for the delta S of the surroundings. The difference, though, is it's actually negative delta H over T. So this is the one that looks just like the delta S of the surroundings. The difference, though, is the negative, because again, with the surroundings, what we're talking about is opposite effect in terms of enthalpy. So this is the one where you don't want to get confused. So we want to use this one here on the screen that's in the box for a situation where we're doing a phase change and we want to calculate something like the entropy of fusion, the entropy of vaporization. We want to use the one with the negative when we're trying to calculate the entropy of the surroundings. So again, don't confuse these two. People always want to put negatives here and not negatives there and stuff like that. So if we were doing this for our phase change going from liquid to gas, for example, going from liquid to gas, we would use our delta H of vaporization for water, which is roughly 2260 joules per gram. And going in that direction, it would be positive, and that would get us, again, a positive value for S for that case. If we happen to be doing the opposite sort of process, we're going from gas to liquid, the delta H of vaporization would be the same number, but it would be negative 2260, which that negative that you would put in there in that particular case would end up giving you a negative value for delta S, and that would make sense as well. Again, going from gas to liquid, we're going to more order. Going from liquid to gas, we're going to more disorder. So we do use this. Sometimes you may actually put a negative in there if the heat of vaporization should be a negative value depending on the direction you're heading. And again, you can do the same thing for fusion as well. So I guess I shouldn't have wrote there, but if we kind of put our values in, the 40.8 kilojoules is the heat of vaporization in kilojoules per mole. And it roughly translates to about 2260 joules per gram. So that's what that number is the delta H of vaporization in kilojoules per mole for water, about 40.8 kilojoules per mole, which again, roughly translated is the same as the 2260 joules per gram, give or take a little bit. So we see here 109 joules would be our delta S value. And again, we would assume that this would be going from liquid to gas. The only difference, again, in this calculation, if we were heading in the opposite direction, it specifically said you were going from gas to liquid, is our 40.8 would be a negative number and thus giving us a negative delta S. Any questions on that? So again, this is the equation that sometimes people kind of confuse and mix together with the one with the negative. So why don't you take a second here and calculate the enthalpy, the entropy of vaporization for mercury. The enthalpy of vaporization is 58.5 at its normal boiling point, which is 630 Kelvin. Let's see what you come up with. Okay, so in this case here, again, we have the delta H of vaporization, which is 58.5 kilojoules per mole, and our boiling point temperature of 630 Kelvin. Remember as well, sometimes we always get fixated for water, for example, and we always think, oh, it's always boiling point 100 degrees Celsius and so forth. Remember that obviously other substances have different boiling points, melting points, freezing points, obviously. So obviously, if you're not dealing with water, you don't want to always just assume, 100 degrees and all that kind of stuff. So again, using our formula here, because we're doing our phase transition, our delta G is going to equal 0. So rearranging that equation is going to give us our delta H over T. And in this case, we will assume that we are going from liquid to gas, and our delta H would be positive. So it's going to get us 58.5 kilojoules over our temperature, which is already converted into Kelvin. So that's good. And if we do that, we will end up with 0.0929. This would be kilojoules. And again, if I multiply that by 1,000, 92.9 joules for our delta S. Again, I converted it to joules because typically speaking, delta S is in joules. And again, it would be a positive number, assuming that transition, if we were specifically told we're going from gas back to liquid through some type of condensation type process. Again, the only thing that would be different, again, you would just put the negative there. That would give you the negative, and that would get you the negative in that particular case. So again, you'll end up with pretty much the same calculation, just like usual when you're dealing with sort of heat of fusion, heat of vaporizations. Really, the only difference is going to be sort of the sign that you end up with. Any questions on any of that? Okay. So I feel like we've neglected our good friend equilibrium constant because we miss K a lot. So let us then talk about K. Good talk. Let's talk a little bit more about it, perhaps. All right. So again, up until this point, a lot of the equations we saw for delta G, there's a few different ways to sort of calculate delta G. And like I said before, there is a number of different sort of ways to calculate delta G, RA delta G sort of fashion. And again, the best sort of route to do that is to sort of use the information that's given to you in the problem. Again, as we see these little knots that are sometimes written on these formulas, again, technically speaking, these little knots are, again, what it means is sort of standard conditions and everything. And usually we talked about those standard conditions, which is, if it's temperature, it technically should be 25 degrees Celsius. If it's pressures involving any type of gases, they should all be at 1 atmosphere. And if it's concentration and stuff like that, it should be 1 molar. Good on this slide? Yeah. So we see another delta G sort of formula here that's a little bit different. It does have 2 delta G values in it, if you will, this delta G and sort of this delta G here. So the difference between it is the little knot thing that we see. And here, this delta G is sort of like what we calculated. So either it will be given to you, if it's not given to you. In most cases, this would mean you would go to the table, take the delta G of your products minus your delta G of your reactants. So you would do sort of the table version of it using the balanced equation and the values that you would find in the table. Again, if it wasn't given to you, that's how you would calculate that delta G. R here is the gas constant, and again, it's the one that involves energy, so it's the 8.314 version of it. T is our temperature, like usual, needs to be in Kelvin. And our Q here is our normal Q. It's our reaction quotient, which again is our products over our reactants. Remember that this is calculated the exact same way as you calculate K. Again, we use our coefficients as exponents, just like we've done with Q before. And what all that gives you is this delta G value over here. Yeah. So you could sort of think of this delta G value as the delta G in non-standard conditions. So again, what that means is something is not like under standard conditions, something is not textbook table type conditions. And really what that means is perhaps the temperature is not 25 degrees Celsius. Perhaps when you calculate Q over there, the pressures aren't 1 atmospheres, the concentrations are 1 molar. You know, there's some type of variation in terms of those standard conditions of, you know, the main ones we've been talking about here: 25 degrees Celsius, pressure is 1 atmosphere, molarity is 1 molar. You know, something there is not of those conditions. And basically what this equation will tell you is what the delta G would be under those sort of non-standard conditions. And that's why we also have in this equation here the delta G naught, which is basically tell us what the normal standard conditions, what the reaction would be. Would it be spontaneous or non-spontaneous? Now, when we do get to equilibrium, this equation up here really becomes this equation over here. And when we get to equilibrium, our delta G will equal 0. And if we're at equilibrium, we're no longer dealing with Q, which is sort of the reaction quotient or anything like that. We are dealing with K, which is the equilibrium constant, right? So if we're at equilibrium, we'll have the equilibrium constant. So basically, the top guy reduces down to this bottom equation here, which allows us to calculate the delta G naught under sort of standard conditions if we know the equilibrium constant. So these are our same values as what we see above. R is the gas constant, the 8.314. The T is the temperature in Kelvin, and the K is, again, the equilibrium constant. So again, these two equations you do need to know. And just like all the other equations there, when you should use them, a lot of times is dictated by the question. So obviously, if it has something to do with what's the equilibrium constant, you're at equilibrium, something I've mentioned about equilibrium concentrations, you know, you should be using this equation. Yeah? If you're not talking about equilibrium, but you're talking about maybe initial conditions, you see things aren't under standard conditions, then obviously you should use the other equation. So again, you want to pick out sort of the one that sort of fits in terms of the information. You know, if you're counting, this is almost sort of 4 different equations that have pretty much delta G in it. We have our delta G where we take our products minus our reactants. We have our delta G equals H minus T delta S. We have our delta G right here when our non-standard conditions. We have our delta G when we're dealing with the equilibrium constant. So again, sometimes people get a lot of confusion as to, you know, which one should I use? So just keep it really simple in that aspect and just think about the information that's given to you in the problem and sort of calculate it using that information. Any questions on that? All right, let's get that. So again, we can look at sort of the information here, but when we're using this equation and really dealing with the equilibrium constant, it's sort of the same idea. If we have a K value that is greater than 1, that means that we should expect obviously products to be formed, right? As we know from just K. But when we do have a value greater than 1, when we take the natural log of it and all that good stuff, we will end up with a negative delta G. And vice versa, if we have sort of a small value of K, just like normal, that means that we should have S. No, we should have reactants that's left there, and that should get us a positive value for delta G. Now, if we have something at 1, again, it means sort of the same thing. You know, you got kind of reactants and products possibly there. They're probably there pretty close to the same ratio, right? That's essentially how you could get a K value is equal to 1, right? Products over reactants basically equal each other. And you have basically the same amount that's there. Delta G would equal 0 in that case. Again, logically speaking here, mathematically speaking, natural log of 1 will equal 0, right? And that will wipe out that entire thing there, and our delta G would equal 0 at equilibrium. So again, at equilibrium, mathematically looking at the equation, now you can perhaps see why we say at equilibrium, delta G sort of equals 0. You can see it just zeroes out basically. All right, so why don't you give this a go here and see what you come up with. Have some values there. Calculate the equilibrium constant, Kp, for this reaction at 25 degrees Celsius. So see what you come up with. Okay, so let us take a looky here. So in this case, we're looking for the equilibrium constant Kp. Remember, it doesn't really matter what equilibrium constant you're looking for. They're all the same. And again, the only one that has really sort of delta G's and our equilibrium is the one that we just saw, natural log of K in this case. We do have the temperature. We do have R. We were looking for K. So we do need to, again, if it wasn't given to you, basically go to the table and look up the values of delta G. And this, again, is going to be a situation where we're not going to do anything weird. We're just going to do our kind of products minus our reactants. And looking up those values, our O2, I didn't give it to you, but remember that anything in a standard state for delta G will be 0. So it's going to be basically 3 times 0 minus our 2 times our 163.4. By the way, these are kilojoules, which is, I guess, sort of important there. And that's going to get us, when we do that, 2 times 163.4. And that's going to give us minus 326.8 kilojoules. So now we do have this number here. And we can go into that equation and solve for K. And if we do solve for K, in this particular case, the natural log of K will equal delta G naught divided by minus RT. Putting our numbers in here, we're going to take minus 326.8. I am, again, because of those units, excuse me, going to multiply by 1,000 to make sure everybody's in the right unit. The reason for that, again, is our R value here is in joules. So everything sort of cancels out correctly. 298 on our temperature. So that will get us 326.8 times 1,000 divided by 8.314, and 298 divided by, it's just something like 131.9, and that's going to equal our natural log of K. We're then going to take the E of both sides, right? So K would equal E to the 131.9. And if we do that, we're going to hit something like a 1.9 times 10 to the 57, give or take with some rounding, depending on where you rounded, will get you the equilibrium constant. Any questions on that calculation? A couple of things do sort of match up in terms of just sort of theory-wise about what we would expect. Here we got a negative delta G, which means this reaction should be spontaneous, should be heading to the product side, and thus we should have a large value of K, and I'm assuming that qualifies as a large value of K, obviously. Any questions on that particular one there? Okay. Oops. All right, so let's take a look. I think got another example, if I'm not mistaken here. Let's see. Yep. So why don't you give this one a go here? Delta G naught for the following. Calculate the delta G naught if the KSP is 1.7 times 10 to the minus 6. See what you come up with. All right, so again, in this situation, we're given the K value. We're looking for the delta G. So we will use our delta G equals our minus RT natural log of K. In this particular case, we actually have everything on the right-hand side. So this one's not bad. It's just a plug and chug type situation here. We're going to take our 8.314. We're going to take our temperature converted to Kelvin, which is 298. We're going to take the natural log of the KSP value. Again, another type of K value. Doesn't matter as long as, you know, it's a K value. And if we put all that good stuff in, we will end up with a delta G value of, I can find where I'm good, right? There it is. Of 32914. Again, this would be in joules based off of this number, which would get you something like 329, or I think I missed it. Get you 32, I'm sorry, 0.9 kilojoules. In this particular case, we have a positive delta G, which means it should be non-spontaneous, which means really this reaction should lie over there at the reactants. And that should mean that our K value should be small, which obviously it is here. So again, all those numbers do make sense in terms of when you think about what is happening in terms of delta G, delta K, delta G, K. You know, all those things should basically complement each other. And this obviously is a KSP, which, as we know, and hopefully know in about an hour, right, is usually things that are insoluble, and usually that equilibrium does lie to the left-hand side. Any questions on that? All right, one last example, I believe. I'm mistaken. Yep. One last example here. The delta G for the reaction is 2.6. We have an experiment where we have partial pressures of H2, I2, and HI. We want to calculate the delta G for this reaction and predict which way it will go. Will it go to the reactants? Will it go to the products? And see what you come up with here. Okay, so let's take a look here and see what we got going. So here we're given the delta G naught. We're also obviously given the temperature, and we're given a bunch of partial pressures here. And we're looking to calculate the delta G of this reaction. So this should lead us again to one of our many choices, but really there's only one sort of formula that will work. And if we go back and kind of look at it, it is again this one here that has really all those components in it. We also know that we're pretty much trying to find delta G without the naught, which basically means sort of unstandard conditions or non-standard conditions. And in our case for this last problem here, the really non-standard conditions here are our pressures, right? So remember, under standard conditions, the pressure should be 1 atmosphere. Here, we're not at 1 atmosphere, and that's why we're going to be looking for our delta G, which would tell us what our delta G would be under these non-standard conditions. And again, so we would want to use that delta G equals delta G naught. Again, also what people mess up, they got the minus all the time. It is plus in this case, RT natural log of Q. And in this case, they actually gave us the delta G value. Again, if they didn't give us a delta G value, would have to kind of go look it up in the table and figure all that stuff out. R is a constant. T is going to be our 298, right, when we convert it to Kelvin. And then we pretty much have everything else that we need. So in this particular case, we would take the delta G is equal to our delta G naught. So 2.60. I'm going to again times it by 1,000 because we're still going to have some issues here because this is kilojoules. Again, this is joules. So again, we still have that sort of unit issue on both sides. And again, you can leave it in joules on both sides. It's just up to you, your preference. 8.314, which I could leave. Our temperature would be 298. Natural log, remember Q is our reactants over products, so that would be our HI. Just like normal, we would have to square it because of the 2, divided by the concentration of our H2 and our I2. Oops. Are the sequel here, number 2. And obviously in this particular case, although I just wrote concentrations of everybody, just like K, you could also obviously do this in the pressures of each of these. So the pressure squared of HI divided by the pressure of H2 and the pressure of I. So remember, you could do it either way, pressure or concentration. So that means on top should go our HI, and we're going to take 0.23. We're going to square it. On the bottom would go our I2 and our H2, which is 4.26. And 0.024. Any questions on that setup there? So 0.23 squared divided by 4.26 divided by 0.024. Take a little natural log action of that. Times it by 298 and times it by 8.314. So if you clean up sort of the right-hand side and the left-hand side here, you end up with something like 2,600 plus minus 1,632.5. And then if we add those together, we're going to end up with 967. And this is going to be joules in my case, or that would be 0.967 kilojoules in this particular case. First off, any questions on the calculation part of it? Now, when we do look at it, what we eventually got here, right, is a delta G value that is positive. And that delta G value that's positive should tell us that it is still a non-spontaneous process. And we should favor reactants in that case, right? Reaction really should be heading or staying to the left. We also see that even under standard conditions, The delta G value, the delta G naught value is 2.6, which is a positive number as well. So even under standard conditions, it's still non-spontaneous. And by playing with these pressures, in this particular case, we did not really turn it into a spontaneous reaction. Any questions on any of those calculations there? And we could also see that as well if you just kind of look at the pressures, the majority of the pressures with H2, which is a reactant. And I'm not sure why the equal is there, but it's a non-spontaneous process. Any questions on anything here from this chapter that we talked about, thermodynamics? So obviously you need to be able to deal with delta H's, calculate delta S's, system surrounding universe. Got to calculate delta G in a variety of fashions, both standard and non-standard conditions. Need to be able to figure out the equilibrium constant as well. Any questions on any of that stuff that we talked about? And again, just a reminder that if a reaction is spontaneous, it doesn't necessarily mean that it is going to happen super fast or super slow. It just means that under those conditions, it will happen. And again, when we talk about sort of fast or slow, that is more dealing with our rates. All right, any questions on any of that? All right, so since we're sort of getting to the end of lecture, I'm not going to start the next chapter today. We will start the next chapter on Thursday. We'll do a bunch of lecturing on some redox and electrochemistry. The notes are up online. Now, you do have a couple of things going on for the rest of the day, I imagine. The first major thing, obviously, is your exam. It will be open up at 11:30. And just like before, you'll need to take it. You'll need to obviously work out the problems. There's a lot of stuff that does require work. So make sure, again, you have your paper, your calculator, and everything that you're going to have the ability to show the work. Once you've submitted your exam, remember that you'll have, I think, 30 minutes. And that's usually plenty of time for everybody. So you have about 30 minutes to upload your work. Make sure it gets in within that 30-minute window. If it does not, I probably will not give you credit for those questions. So make sure that you do get it up there. In addition, you do need to submit an answer for every question that's found online. And the answer that you submit does need to match the work that you show. And again, if those two things do not match, you probably won't get credit either. So make sure that those things do match. You can't, again, submit crazy answers online and just go, oh, I magically worked it all out perfectly on the paper afterwards. So it does need a match and everything like that. There will also be a spot where you can upload your homework from the textbook that will be separate from the exam module. So I think it's listed with upload your work type of area and stuff like that. Same type of situation. You also go, you look at the academic honesty agreement, sign it electronically if you like, or again, you could print it and upload it as well. That will free up the exam to take. Once you take the exam, you will then obviously have time. Remember that once you start the exam, you cannot stop the exam, the timer, or anything like that. So make sure that you're prepared to take it, because again, even if you click away and come back, the timer will still go and it will not be reopened for you in that particular case. Also remember that you need to submit the exam just once. When you're all completely done, you've answered everything. Again, if you do it before that, it will give you a warning that says, are you sure you want to do this, because you haven't answered a bunch of questions. But make sure you only submit the exam once. If you submit it wrong, it will not be open for you again. And again, a friendly reminder, there are different questions, there are different versions and everything. So like a normal exam, don't have the right answer on the wrong version. That's not going to end well for you as well. So make sure you don't do anything dumb like that as well. So that should take care of the exam. Also, just a reminder, most everybody should be starting pretty much at 11:30. That is when we normally would take it, and that's when you should normally start it. If you start it at 11:30, you will not run out of any type of time. If for some reason you decide to start it later than 11:30, remember that if you start too late, the computer will cut you off at some point, and you may not get your total time. So make sure that you do start it pretty much at 11:30. That won't be an issue. Again, if you for some reason decide I'm going to start at 10 minutes before the cutoff time, it's only going to give you 10 minutes to take that exam. So, and again, it definitely will not be reopened for you in that situation either. So make sure that you do start it pretty much around 11:30. You don't start exactly on the nose at 11:30, but pretty much on that point. You should not run into any of those issues. Any questions on the exam part? Okay, now you also do have a lab, the buffer lab, which I think was moved to technically be due today, and that is still technically when it's due. Just to let you know, I think all of the submissions for that buffer lab, in terms of being able to submit things, even if it's past the due date, it should still let you submit it. So if for some reason you haven't completed it, since it's been up for over 2 weeks now, I think, if you haven't completed it and you're still going to complete it, even if the due date has passed, it will still accept your submission. It will just mark it late. So you don't have to pre-ask me. You will probably still accept it if it's tomorrow or something like that. And again, when I go to grade it, I will look at the submission date and time and make the appropriate decision on credit based on that. So just to make it easier for everybody again, and myself, if you happen to have maybe not completed all parts of it or still have something that needs to be turned in, you can still submit it past the due date. Again, it will be marked late, and I will make that decision in terms of how late it was, in terms of any appropriate sort of point alterations based on how late it is. So I would try to get it in. You really should have it in. It's been a long time on that experiment. So make sure that you do get it in. And even if it's late, make sure you do turn it in. Some points are better than none. Yes. So make sure you get it in at some point before June. Yes. I'm just kidding. Way before June. All right. That also means that next week, I think the titration experiment is coming up. So if you have not been working on that, I suggest you start working on that so we don't run into any situations like that. We're going to, in terms of, we're going to, I think, you would have to check online. I believe it's the 15th. I have that date in my head for some reason. So the titration one, I think, not the 15th. I don't think that seems wrong. Maybe the 19th, I think, 15th or 19th, or one of those days. It'll be the 19th for sure. I'll move it to the 19th if it's not, but I think it's the 19th for the titration one. I think it may be 19 right now, but the next experiment is about redox and stuff like that. So to answer your question about the next lab, I'm not sure if we'll officially start it on Thursday during lab time. We may do some lecturing, both in lecture and some lecturing during lab. And then maybe after the lab lecture, you'll have enough information to start at least the electrochemistry experiment, I think it is, or the redox reaction one. So I think that's sort of the plan for Thursday. We're going to do some lecturing, kind of see where we're at. And then in terms of the experiment, because it is on, I believe, redox and kind of electrochemistry, we'll take a look at that. Yeah, the titration report is a full lab report, yes, on that one. And again, that will be the last sort of full lab report, I believe, for that one. So the buffer one was pretty much just submit all those sheets that you needed to submit, each of those kind of individual sheets, and that was the lab report for the buffer one. And then for the titration one, it will be it will be a sort of formal type report. Notebook pages. Let me think. Yeah, I think I think they had some notebook pages, I believe, for the titration one as well. Yeah. So, and in terms of your question, the notebook pages that you could turn in are the notebook pages I think they made for the titration experiment. There's no online submission, so you'll take it like you would take your carbon pages and kind of submit it with your type lab report when it's due. But you could use those pages that they made as your notebook pages, and then you could just submit it with your type lab report. Yeah. trying to remember. I think they made kind of like notebook pages for titration one as well. So yeah, so you can use those. It could be submitted with your lab report, kind of like normal, like you rip out your carbon pages and kind of submit those in to it. Other questions on that? Okay, so that's the titration lab again. If it's not the 19th, it will be the 19th when it will be due, I believe. So that's a week from today, I think. And like I said, we'll take it on Thursday. We're going to do some lecturing, see where we're at. And then at some point, either Thursday or maybe after lab on Thursday, the next experiment will be open for you to start working on. You know, because again, it's all deals with redox and stuff, which is the next chapter. I think the last thing that we need to talk about, I think, is the project. So again, I went through and I approved pretty much everybody's first selection, I believe. Like I think I said the other day, so you could continue working on that. Remember, you got like a month, I think, ish, until we kind of do those last couple of lab periods. We're going to do those presentations. I think everybody got their first choice, maybe except for a couple of people got their second because there's a couple of overlaps in terms of topics and stuff like that. So if you have any issue with the one that was approved or anything like that, and you maybe want to change it to something else, you know, you could just email me and I'll look at it and stuff like that. But otherwise, you know, you could look on there. You should be able to see that it was approved, the topic that you submitted. Any questions on any of that stuff? Okay, so the last thing is, again, make sure, again, you follow each of the instructions on the exam, especially the instructions for every single question in terms of how to enter the answer. So make sure that you do enter the answers, how it asks you for each specific question. I would say, again, a reminder that when you do submit the exam, the score that you see is probably not the correct score until I've had a chance to look it over. So just keep that in mind as well. Again, I will go back and look at the computer sort of grading to make sure it didn't mark anything, you know, kind of weird because of the way you entered it and stuff like that. So take it with a grain of salt, the score that you get at the end. And again, it may change, as you probably have seen from the previous stuff that we've done. And again, a reminder, make sure you start the exam at the appropriate time around 11:30. And if you do need any type of question that I can help you with that's unclear, which I don't think there's very much that should be unclear, you can email me through Canvas and I will try to get back to you as soon as I can. If for some reason I miss it, just make sure, just continue on obviously with the exam and do what you think would be appropriate. And then obviously you can make a note somewhere and let me know if something was weird or something like that. But you know, I'll be monitoring my email and I'll be able to get back to you pretty quickly, but just in case, you know, just continue on with the test. Don't just stop. Okay. All right. Any questions on anything? Okay. So obviously no lab meeting officially for today. Go take your exam and we will be back here on Thursday for live lecture, which we will continue on to the next chapter, which is electrochemistry. All right, good luck on everything, and I will see you on Thursday.